So welcome to the static Kotlin bug hunting with K2. So here you're going to hear a little bit about static code analysis for Kotlin. Just a quick check. Raise your hands if you are familiar with Kotlin. Oh, perfect. Okay, so I don't need to explain you the language now. I have to cut my presentation then. Let me introduce myself. My name is Marharyta. I'm a staff software engineer at a company called Sonar. Do you know SonarCube? So I'm the person writing static code analyzers for various languages like Java, Kotlin, Scala, also recently Dart, and some more. So yes, I'm the go-to person if you have problems and you want to discuss if we are doing a great job or not really. And this is my handle that you can find me on various social networks like Twitter, Blue Sky, LinkedIn, or almost everywhere. I am as Marharyta N. So, how it all started. A year and a half ago at Devox Belgium, I did similar tools in action called static Kotlin bug hunting. And it was fun. It was more hands-on way to write your own static analyzer, so you learn how it works under the hood, what it's doing. And while I didn't get that many participants at Devox, a lot of people became interested in the talk and wanted me to repeat it at various conferences. However, at the same time, there was one more thing that happened that made almost half of the talk irrelevant. This is K2. Do you know what K2 is? So in May 21st, 2024, right before the Kotlin Conf last year, Kotlin 2.0 was released. And while for users, it was almost nothing changed. The transition was more or less okay, at least for the most of my projects. It was a huge change for the tools, for everybody who are using compiler. Because the thing that they did, they replaced the old compiler with a new compiler. Compiler front end. And the tools like us, like other static code analyzers and maybe code generation tools that heavily rely on compiler have to technically rewrite everything and forget everything you've been doing before. Now you need to do new stuff. And it means that I cannot repeat honestly, the talk that I did 1.5 years ago, I need to completely change the content. So it took some time for me, firstly, to migrate our analyzer to K2, and then to prepare this talk that will now include the K2 compiler here. So what we're going to learn today. First of all, some static analysis intro, because I don't think that's the subject that most of you know. So some introduction, then we'll implement the first rule. Then we'll spend more time on what is semantic model, what we can do with this, and what actually changed with K2. And there will be a few takeaways. So first, how static analysis work. As a parent, I think the best way to explain things is to explain things by example. So here it is. Let's imagine we have some simple class, hello world. It has one function, and it has a statement inside which prints hello world. How compilers work and how static analysis tools work. They took your source code and they parse it according to their grammar, and they output some, firstly they would put some intermediate structure, and usually the structure is called abstract syntax tree. It is a tree that contains nodes that represent this or that language structure. For example, you can see here function, you can see parameter list, you can see left brace, you can see statements and call expressions, arguments, and everything very precisely. Then there are also a lot of other steps, like other intermediate representations, and finally it will be transformed either in bytecode if you're on JVM or maybe in some native code. And then at the runtime, it's executed. For static analysis, we don't need the other part. We need this AST, and for us, it's enough. We take this AST, and then we run visitor pattern on these trees. And in these visitor patterns, we usually implement the rules. And the rules mean like finding some interesting pattern in this tree. And if it triggers, this will be, the rule will trigger as well. As this is a tree, in my presentation, we'll often refer to it like this. So I don't show you that ugly structure. And these are, for example, the issues that static analyzers can report. For example, by looking at this abstract syntax tree, we can find things like something is unused, there is some to-do comment, or there is a like piece of dead code or something else. Like we can find a lot of interesting things in the abstract syntax tree and report you to them as an issue. So in simple way, static analysis looks like this. It takes your source file as an input, transforms this into the tree, and then like outputs some issues that we could find here. So as it's tool in action session, let's write some code. And because we don't have much time, and I already wrote some code for you, so I had some demo example, which contains some skeleton for static analyzer. It's open source on my GitHub. I'll share the link so you can play with it afterward. So here it is. Usually at work, we start with a test. So for example, we want to write a rule that detects that the function has a good or bad name. For example, according to convention, good name is a good name, bad name violates the convention, so we report an issue. And this is the notation that I come up by myself, like it's not the same notation we use at Sonar, but similar. So this is how we will indicate in our test file that here is an issue. Like this is the rule code, this is the rule message, and this is the location, third line, 5 column, till third line, 13th column. And this is version name. And this is our stupid simple implementation. We visit named function. We assume that named function have names, because it's called named function. Then we say that like if the name matches the regex, it's fine. If it does not, we add an issue. So let's test our rule. Here is a test. So test, it just executes this rule on this source code that I showed you. Test passed, so everything is fine. So we just implemented our first rule. It works. We should be pretty proud of ourselves. And as we always do, we go to our colleagues, show like, okay, now we have some like first rule in our own static analyzer, you can use it. And of course, you all have that colleague that will try your code and say like, it's broken, it doesn't work for me. What's not working? You say like, I took your bad function name rule, I tested it with an anonymous function, and it did not work. So let's check it. Let's go to our, let's create another example. Here it is. I created exactly the same example that we did. And let's go back to our test and change the test file to the second one. So let's run the test again. It failed with a null pointer exception. Okay. Where it failed? Here. So, you know, they said that in Kotlin you won't have null pointer exceptions, yeah? But you can have null pointer exception if you're stupid enough, as I was. So, of course, I put non-null assertion. It means that I said, I definitely know name is rare because I assumed that KT named function will always contain the name. And then, after talking to JetBrains people, they're like, what? Why? And here is the fun fact that KT named function is the function that is declared with keyword fun. It doesn't have to have the name. So anonymous functions are also KT named function. So this made me learn that IST tree for Kotlin is not ideal. And sometimes we face issues like this. It's not the first issue that we faced, but there are a lot of like unintuitive things. So we should keep in mind that kt named function is not always named. And yeah, so we can refactor it. I already did it like this. So we can see that, okay, name can be nullable. So we only report if it's not null and if it has and if the name does not violate the convention. So let's get back to the test. Let's change it to the first one. And we have a second test which checks the new implementation on the old test. So here it is. Let's run this one. And this should pass. Yeah. So it passed, no null pointer exception. So we fixed the first issue, and we a little bit learned what we are doing at Sonar, like addressing you the feedback that you give us in community forums and all the ones that we find by ourselves. But come on, but function name is a very stupid simple rule. Let's implement something more useful. And with the recent migration from K1 to K2, and from the old compiler to the new compiler in our analyzer, there was like a bunch of rules that took most of my effort. Like, 20% of the rules took 80% of our effort. And one of such rules was mutable collections should be immutable. Like, I think this rule took all of me when I was rewriting it. So what the rule is about? Sometimes we create collections, and you know that in Kotlin your type can be just simple list or mutable list, or simple set or mutable set. And in mutable collections, you have functions that mutate the state. And in just list, these functions are absent, so you cannot mutate the state. And we assume that immutability is a good thing, so by default, things should be immutable. So how do we want to detect the necessary mutability here? We will visit the function, then we will visit the first statement. We create the list of a mutable type. We see the first usage, and this is the only usage. This usage is a read, so it does not mutate the state. It means that list 1 can be immutable in this context. So we can report issue here that you can replace this list from immutable list of to just list of. And then we will check the second list. We'll find out that there is list end, so we cannot replace it easily with list of because we will break the compilation here. So here we won't report an issue. And recently JetBrains released Juni. I asked Juni to implement the first version of this rule. So let's see what it did. First of all, this is our test. So you can see the list. There are the same notation that mutable collections should be replaced with list. Like there is issue here because we only print, and there is no issue here because we mutate here and there. So pretty straightforward. And this is the first implementation. Okay, I think it's easier to go here. The first implementation that Ginny showed me. So first line looks fine. It takes type reference. If there is no type reference, we return because we are not able to identify the type. And then it does very strange thing. Takes the line number and says that if the line number is higher than 13, then we'll don't report an issue. If it's lower, then we'll report an issue. So instead of writing the actual rule, it was trying to cheat my test. So then I adjusted the prompt, say like, Juni, please don't do this, write the correct implementation. So this next implementation was like, okay, there are mutating operations, we hard code them. We take the type reference, and then we check that if it's a mutable list or mutable set, and then if the operations that are used on this are in these ones, are mutating the state, then we don't report an issue. If there is no operation from this list, we will report an issue. And if we run our test, let's check, it works. So it works, yeah. Okay, congratulations, it was our second rule. And then, again, this annoying colleague. Something is not working. And of course, it's often like this. It's just the first implementation, just the first iteration. It's not ideal. Of course, there could be some false positives, false negatives. So let's have a look what this colleague found. And found like, OK, when we just use the library functions, it works fine. But for example, I have my own function mutate, and then your implementation doesn't recognize it as a mutating operation, and we report false positive here because we assume that there is no mutating operation here. I'm like, yeah, OK, let's fix this. And before we are able to fix, now we are getting to the most interesting part of the compilers. It's a semantic model. So again, by example, what semantic model is. Remember, we had this class, hello world, with a function. And let's imagine that in some other file, we have a function g that takes a parameter of a type hello world and calls the function f. Without semantic model, for us, there are two different things. Like, we don't see any connection between two files, between two classes. So for us, we don't know that this x is of this type hello world. But semantic model is like the structure that helps us identify this relationship. That we understand that this type is actually that type, it contains this function that has that signature, and we can even go inside if we have it. So these are, like, we can understand that this function call is actually from this function declaration. So this is what semantic model is. Like, in more simple words, in the terms of trees, it's like a forest of trees that contains also relationships between different trees and between different branches of a single tree. So before K2, in K1, in the Kotlin compiler, it was implemented via binding context slices. So binding context is the structure inside Kotlin compiler that was split into several slices. Each slice had a name, for example, type, reference target, resolved call, and so smart cast. And each slice is sort of a map. Is a map that represents, that has a key, some KT element, so some node from the AST, and the value could be other node from the AST, some descriptor or constant. For example, slice could be named like compile time value, and we can say like this is some compiler constant, so KT element of a constant, and then from this slide we can find out the compile time value of that constant. So the same way we can find out the types, we can find out the descriptors and the signatures of methods, and so on. The problem here was that you need to know the slice name in advance. The problem with this is that it was not really like very well typed, described. So every time we had to get something from binding context, we had to guess. We had to guess where it works for us or does not. So working with binding context was tough. And another problem, it's compiler internals. So it's supposed to change, or how it happened in case of K2, completely disappear and be replaced by other compilers. So this is how we worked before. Then, what happened with K2? With K2, JetBrains and Kotlin creators decided that, okay, probably that's nice, that we are not just like allowing people to use our internals, but let's create an API for static analyzers, for plugins, for like any other use case who want to integrate with us. So let's have something that will be more official. So this is how Analysis API was like created. And the interesting fact that Analysis API can also be worked both in K2 and K1 mode. And it's like a slow migration between K1 and K2. So you first migrate to Analysis API, and then you switch from K1 to K2. So this is what we did at Sonar. Analysis API, I guess it's still not finalized. So it's still experimental, so we are all using it on our own risk. But it's closer to its final state. And it has at least some guarantees, it has documentation, so it's a much better way of writing. Like with the only problem that in order to migrate to Analysis API, we had to rewrite almost all our rules to this. So, how it represents. Analysis API is more closely to other compilers that we worked for at Sonar. For example, for Java we use ACG, and in ACG the main thing is a symbol. The same for Analysis API. The main citizen there is a symbol, and from symbol you can get other stuff like types, signatures, soft calls. Of course, it's very roughly. Of course, you're not always going through symbols, but it's very nice that all the symbols are typed. For example, from type, you can only get type symbol. From class, you can only get a type symbol, or from declaration can be declaration symbol, and you can only get the things that are relevant to this on that structure. So it's much easier to work with. Okay, I think I'm talking enough. Let's get and fix the issue that we had. So here it is. Maybe it would be easier to understand what happened if I just do the diff. So what we did, we assumed that function is mutating the collection if the parameter that it's taking is a mutable parameter. For example, if its function takes just a list, we assume it will not have access to the mutating functions. And if it takes a mutable list, we assume that we'll use the internals of mutable list, we'll add and do some other mutating operations. Of course, it's heuristics. Of course, people can do some casts. Of course, people can cast everything to Java array list and then can do what they want. But we assume that, okay, if people don't violate the signature, we can use this heuristic, and in 80% or 90% of cases, it's going to work. So what we do? First of all, here, in order to get this Analysis API, we need to use the function called analyze. And inside the analyze, you immediately get lots of extension functions, and that are giving you resolved calls, symbols, and other things. So here we can see that we are getting the parameters, and then we are checking the type of the parameter, and we are checking that the type of the parameter is not a mutable collection, like it's here. So if it's iterable list, set, and collection, we assume that this is not mutating operation. But if it's something else, we assume it's a mutating operation. And then let's check if that works. So here it is. So this is the third implementation, and this is our example. So this is function mutate, where we should not report an issue. So let's run the test. And okay, it passed, so it means we fixed the issue. So, of course, it was not the last issue. Of course, we had more. So what happened? This time, raise your hands if you omit type declaration in your declarations. If you write list equal mutable list of, and you don't put type declaration. Don't be shy. It's not a sin. We all do this, because in this case, it's obvious that the inferred type is mutable list, and Kotlin has, can infer types, so we can omit this. And of course, we have false negative here, because literally here we can say that it should not be mutable, but we cannot report this issue because we omit type declaration. So let's fix it. Here it is, our next example. So you can see that here we omitted type declaration, and we never reported it. So let's get to our implementation and check what's actually changed. And here it's a small change, so you see only a few lines of code changed. So you remember how in the past, we've been taking the type. We've been using type reference, and if there is no type reference, we returned. Now, we can fix this. We can go and use the analyze function, so we activate analysis API, then we go get symbol, return type, and from this return type, we can get the class name. So instead of getting the class name that you declared in the type reference, we can actually find out it from the semantic model. And then this type is more precise. And once we get this type, the whole other logic is the same. So, yeah. I think I only changed a little bit the issue reporting because we don't have always type reference, so we cannot always report on type reference. And let's check this, the next test. And of course, I know that 30 minutes might not be enough to get into all the code. So no worries, I'm sharing the link so you'll be able to play with the code you want. I'm just here to show you like general overview, so don't be afraid if you're not getting all the code at the time, because I understand might not be that obvious. So it passed. It means, again, we fixed the issue. Do you think that's it? Do you think it's the last issue in this rule? Of course, we hope, because we have 3 minutes left. But of course, no. Like, some people do things like this. And of course, our implementation doesn't take it into account. So, and of course, we have FP here because we don't see that this is a mutating operation. And I think we have 3 minutes left, so I can skip this example, can fix it. And of course, it's not the last issue, but it was the last issue I showed you. What else? Let's just think about what else can go wrong with our implementation. First of all, how about children of mutable collections? For example, we can extend mutable collection, and our implementation doesn't take this into account. So we have to fix this. We have to understand that the type is extending mutable collection, so it also can be reported. Another thing, we didn't take into account that you can extend mutable list or mutable set, and you can say that this is a new mutating operation, this is a node, so this is non-mutating operation. And we don't take it into account. We only take into account the functions that take mutable collections as parameters. Type aliases. What if we won't work with type alias? Because it will refer a different type than we wanted. We didn't support mutable map. And like, there are a lot of things that you can improve, and it's like static analysis, it's like a never-ending story of balancing between false positives and false negatives. So we don't annoy you with the issues that are irrelevant, but at the same time, we still want to report you something useful, because like the ideal rule, it's just a blank rule, so it reports nothing. But what's the point of static analysis then? So we have to balance between the quality and precision. So it's time to wrap up. Let's look at the achievements, what we did today. First of all, learned how static analysis work. At least now you have some general overview. We wrote static analyzer in under 30 minutes. We integrated with the Kotlin analysis API, so we even implemented the rules. And we learned how to fix issues in the rule implementations, like false positives and false negatives. And there are a few things that I want you to take away from this presentation. First of all, this is the key point here. Sonar Kotlin analyzer is based on Key 2. It was a huge work, so I could not say this here. And then static analysis for Kotlin is fun because of all these extension functions, operator overloading, and all other interesting things. Static analysis for Kotlin is sometimes pain, but usually fun. And be active community member. Or in other words, never underestimate the power of complaining, because while like it could be your colleagues, but in general at Sonar, it's usually you, like people who are using us, reporting in community forum, a lot of interesting issues, and we are fixing these false positives and making the analyzer better, and I think the software in general better. So if you face some false positive, false negative, don't hesitate to write down the community, and we'll try to fix it as soon as possible. And here are all the links, like my previous presentation, the project, and analysis API if you are interested, because it's not just for analyzers, it's also can be helpful if you're writing compiler plugins. For example, KSP is using analysis API, which is Kotlin symbol processing, and or even if you're doing some IntelliJ Kotlin plugins. So it will be useful for you. And thank you for listening. I hope you learned something new today. That's it.